Hi, my name is Luke, and today I'm going to tell you about our experience with applying formal verification to the BPF JIT compilers in the Linux kernel. BPF is a widely deployed language for extending the Linux kernel in various ways. Applications can download BPF programs to the kernel to do things like packet filtering, write tracing programs, express sandbox policies, and more. In-kernel JIT compilers translate the BPF programs to native machine code for better performance. The correctness of these JIT compilers is critical because the machine code they produce runs directly in the kernel and is responsible for making decisions throughout the kernel. This makes them an attractive target for applying formal methods. Over the past couple years, we've seen a tremendous amount of work from the community on applying formal verification to system software. In this talk, I'm going to tell you how to apply formal verification to the BPF JITs in the Linux kernel. There's a couple unique challenges associated with verifying these BPF JITs. First is that they're not designed for verification. For example, the BPF JITs in Linux employ many sorts of optimizations that may be tricky to verify. So we need to develop a practical specification of JIT correctness. And by practical, I mean it's capable both of preventing real-world bugs, but also enabling the optimizations that we see in the JITs in Linux. Second is that the JITs in Linux are rapidly evolving. They're having new features being continually added to them by the Linux developers. And we need to scale automated verification to JIT compilers so we can catch up the verification with these new features as they're being added. Lastly, is we need a way to integrate these JITs with the existing kernel development flow. To do that, we write JITs in a domain-specific language designed for verification, and then extract the C code that we can submit to the Linux kernel as patches. And the goal here is for the C code to be auditable by the Linux maintainers without requiring a background in formal methods. Incorporating these ideas, we've developed Jitterbug, which is a tool for doing automated formal verification of BPF JITs. And it has two main parts. First is a specification for reasoning about JITs, and second is an automated proof strategy. We've applied Jitterbug for various purposes throughout the Linux kernel. First, we use Jitterbug to write and verify a new BPF JIT for 32-bit RISC-V, which has been upstreamed as of Linux 5.7. Second, we've applied Jitterbug to existing JITs for 5 other architectures to find and fix new bugs and to write new optimizations. Our experience with using Jitterbug has also led to clarification changes in the RISC-V instruction set manual. This talk is going to focus on Jitterbug specification, and for details on the automated proof strategy, you should see the paper. Before I get into the details of the specification, let me give you an overview of the compilation process used by the BPF JITs in Linux. First, an application submits a BPF program. An in-kernel checker ensures that the BPF program is safe to execute in the kernel, for example, that it always terminates. Then, the JIT compiler translates this BPF program to native machine code. Therefore, the JIT compiler only has to concern itself with safe BPF programs. At runtime, the machine code produced by the JIT is called like a regular kernel function. It's called with some input data as an argument. There's a prolog that saves registers and sets up the stack, a function body, which can read and write kernel memory or call kernel helper functions, an epilogue, which unwinds the stack and restores the callee save registers, and finally, it terminates with a return value back to the kernel. To understand what sorts of bugs can be made while people are developing BPF JITs, we looked at the history of the BPF JIT development over the past 6 years. What we found is that there have been 82 JIT correctness bugs in the JITs for 5 different architectures. And these bugs exist in every category of BPF instruction, which makes it difficult to do exhaustive testing. To give you an example of what one of these bugs looks like, here's a snippet from the x86 JIT for compiling the BPF instruction, which loads a 32-bit value from memory. I haven't shown you the entire part of the JIT. This part is just for omitting the machine code to clear the high bits of the destination register after the load. First, the JIT has an optimization to avoid clearing these bits entirely if an analysis passed by the kernel deems it okay. Otherwise, there's 2 cases. First case is that the BPF destination register is spilled to the stack, in which case it emits code that loads a 0 to the stack location. Otherwise, the destination register is mapped to a physical hardware register, in which case it emits a 0 immediate directly to that register. There's actually 2 bugs in this code, which are quite subtle and difficult to spot. First is that the check for the optimization is inverted. As it's written, this JIT will evaluate the break statement if the optimization is disabled, which means if the optimization is disabled, the values of the registers after this will be wrong. Second bug is that it doesn't correctly encode an x86 move instruction. The x86 move instruction expects there to be 4 bytes of immediate, but this JIT only provides 1. And this means the first 3 bytes of whatever instruction follows this in memory will be consumed as an immediate, which breaks the whole stream of instructions, which is quite dangerous. So what we've seen is an example of why writing correct BPF JITs is difficult. This is because the developer has to think about code that runs at multiple levels. They have to think about the JIT configuration, such as optimizations. They have to think about the control flow in both the JIT and the emitted code. And they have to think about the semantics of the source and the target instructions. So what we need is a specification that's capable of ruling out all of these types of bugs. This strategy that is adopted by Jitterbug is a restricted form of compiler correctness. And the intuition behind that is to say that the machine code produced by the JIT must have equivalent behavior to the source BPF program. Now, let me describe to you how Jitterbug formalizes this. So we start in Jitterbug by reasoning about any safe source BPF program, any JIT configuration such as optimizations, and any target program produced by the JIT. Then we start with some input data, such as a packet. If we provide that packet to the source BPF program, it'll transition through some number of states, producing some externally visible events along the way. And by events, I mean memory loads and stores or function calls to the kernel. Eventually, it'll produce a return value. Likewise, we can do the same thing to the target program. Provide the input data, it'll transition through states, produce events, and reach a return value. The high-level intuition here is that the specification should require that the trace of events produced by the source program and the target program should match, and that the return values from both programs should match. And this gives us a strong guarantee about the equivalence of the source and the target programs. But of course, the target program produced by the JIT doesn't run in isolation. It has to run with the rest of the kernel. And therefore, the execution of the target program needs to preserve some additional properties that we call architectural safety. For example, the target program should preserve callee save registers. And the way we encode this is an architectural safety property that relates the initial and final states of every execution of the target program. The advantages of this JIT correctness specification are that it's intuitive and that it's effective at preventing many different types of bugs. It's also tailored for in-kernel execution via the architectural safety property. The disadvantage is that it's not amenable to automated verification because it's difficult to encode to an S&T solver. The idea that we use in Jitterbug is to exploit the existing structure of the JITs in Linux in order to come up with a better way of breaking down the JIT correctness property. The JITs in Linux work in a per instruction way. They start by emitting some prologue. Then for each BPF instruction, they separately compile it to some sequence of native machine instructions, and then they emit an epilogue. Jitterbug exploits this per instruction JIT property by breaking down JIT correctness into the correctness of each translation step. So to show JIT correctness, we show that the prologue is correct, that the correct JIT is correct for each BPF instruction, and that the epilogue is correct. And the advantage is that this is amenable to automated verification because these properties are encodable in S&T. Of course, scaling automated verification is still difficult because it requires reasoning about the symbolic machine code produced by the JIT, whereas prior work deals only with reasoning about concrete code. For more details on that, you can see the paper on how we scale verification. We've applied Jitterbug for various purposes within the Linux kernel. First, we've used it to develop and verify a BPF JIT for 32-bit RISC-V. We wrote the JIT for 32-bit RISC-V in the DSL for verification and then extracted to the C code that's in Linux today. We started this effort in 2019 and co-developed the JIT with the specification and proof technique used by Jitterbug over roughly 10 months. From the time that we first submitted it to the Linux kernel, it took 5 iterations of code review before being accepted in March of this year. Automated verification enables us to catch up with features like the zero extension optimization we saw earlier and the more than 100 opcodes that are in BPF. We've also applied Jitterbug to improve the existing JITs in Linux for 5 architectures. We manually translate their C code implementations to the DSL, which takes less than 3 weeks each. During this process, we found and fixed 16 new correctness bugs across 10 patches and developed and verified 12 optimization patches for these JITs. And this demonstrates the effectiveness of the specification that we're able to find bugs in this well-tested code. In conclusion, we hope this is an interesting and useful case study of applying a formal verification to the BPF JITs in the Linux kernel. Jitterbug is a specification plus an automated proof strategy that is effective for developing new JITs, such as the 32-bit RISC-V JIT, as well as improving existing JITs via bug fixes and optimizations. It extends our previous work on automated verification to a restricted class of JIT compilers, which is useful for the Linux kernel. Thanks.